Welcome back to another tutorial on business statistics in Excel. In the previous tutorial, I explained the binomial distribution as part of discrete distribution. In this tutorial, I'm going to talk about the second type of discrete distribution named as Poisson distribution. The Poisson distribution is used to model the number of times an event occurs within a fixed interval, such as the number of emails received in a day or the number of accidents at an intersection in a month. If you notice, at each of this example, we had a concept of interval like an hour, a day, a length in a fabric, or a month. So instead of counting trials, which we had in binomial distribution, in Poisson distribution, we focus on the rates per interval. To use Poisson distribution, three main conditions should hold. First, the number of successes within a specific time or space interval equals any integer between 0 and infinity. The number of success counted in non-overlapping intervals are independent, and the probability of success in any interval is the same for all intervals of equal size, as is proportional to the size of the interval. This is the Poisson distribution mass function or the probability function. Mu is the average number of occurrence in the interval. X is the number of occurrence in an interval. And f of x is the probability of x occurrence in an interval. E is the exponential number 2.71828, and x factorial is the multiplication of x by any lower number up to 1. Like any other probability distribution, Poisson distribution also have a mean and variance. Let's look at an example. Let's assume that in average we expect 10 patients arriving to the emergency room every hour. So interval here is known as every hour. We have the average arrivals, and x can be defined as the number of arrivals in the next hour or in a specific hour. We can find any type of probability, such as probability of receiving 5 patients into the ER, which is a non-cumulative probability as we discussed in binomial distribution, or we can find the probability that less than 5 patients come to the ER in the next hour, which is basically a cumulative probability. We can use the probability mass function for the Poisson distribution to calculate the probability that x can be exactly 5, and that's when we input x as 5 in the function. Mu, or the average, is 10, and e is the exponential number, and x factorial is 5 multiplied by 4 multiplied by 3 multiplied by 2 and multiplied by 1. So if we calculate this function, we can get 3.78% is the chance of getting 5 arrival, knowing that in average we expect 10. The average arrivals is our expectation and it is based on the historical data. But this cannot happen for 100% of the time. Sometimes we get more than 10, sometimes we get less than 10. Let's address this problem in Excel. Again, this is the probability function for Poisson distribution. We have the occurrence of successes in a specific interval. X is the number of success in that interval, and we are looking for f of x, probability that x patients in this example entering ER every hour, which is basically our interval. The average patients that we expect, let's say, is 10. Now, the probability that we get 0 patient, while in average we expect 10 patient, is equal to Poisson dot dist. Again, Excel function asks you for what it requires. It requires the target value or 0. Let's put A18 for the selection of the cell, comma, in average we expect 10, and it's false because we are looking at the probability of x being equal to 0. So it's non-cumulative. So the probability of getting 0 patient is very small, almost 0. I can repeat this for the other numbers as well, up to 20. and also make sure that the graph shows all the numbers. So as you can see, this is a Poisson distribution. You can see that it's almost like a normal distribution with the mean of the 10. As we move toward the average or the expected number of patients entering ER, you can see that the probability will increase. As the X value moves away from the mean, the probability of getting that value decreases up to it gets to 0. So the probability of getting 0 patient is 0. The probability of getting 9 and 10 patients is the highest, and then it decreases towards 0 again. Similar to binomial distribution, this is the non-cumulative probability where we are looking at the probability of X getting exactly one of this value. We can also calculate the cumulative probability. For example, the probability that X is less than equal to 5. So that would be equal to Poisson dot dist 5 patients every hour when we expect 10 patients, and true as for cumulative when we assign a range of value to X. So basically 6.7%. If I add this number, these bars together, that would be the same probability. Basically, if I add this numbers, that's the same cumulative probability, because probability of X less than equal to 5 is same as if I say the probability that X is 5 or 4 or 3 or 2 or 1 or 0. So basically I can add these numbers. So I can say sum of these probabilities. You can see that we can get almost the same number. Or I can also calculate the between probability. What is the probability that X, for example, is between 6 and 12? So in order to calculate this probability with Poisson distribution, we go with this calculation. So probability of X between 6 but not include 6, it starts from 7, and less than 12 but not include 12 is this probabilities. So I can rewrite this probability as probability of X being between 7 and 11. So if I want to calculate this, either I get a summation over this number or using a general rule. For the general rule, we basically subtract this numbers from this number. So I can rewrite this as the probability of X being less than equal to 11 minus the probability of X being less than 7. Probability of X being less than 11 are this number. I'm going to just show or highlight the cells on the right of it just as a representation. So are these numbers, are this range of the numbers. So if I add this number together, then that gives me the probability of X being less than equal to 11, which includes 11. Probability of X less than 7 are these numbers. So if I highlight this as purple, are these numbers. So if I subtract the purple area from the whole range of the blue area, this area, that gives me the yellow area. I can rewrite the probability of X being between 6 and 12 as the probability of X less than equal to 11, or this area, the blue range, minus the probability of X less than equal to 6 or less than 7. X less than 7, which is this purple area. Then it gives me the yellow area, which is my target. So I can write this as Poisson dot dist 11, when in average we expect 10, and it's cumulative, minus Poisson dot dist 6, when in average we expect 10, and again it's true. Poisson dot dist, okay, I made a mistake here. So it is 56.6. It's same as if I get a summation over this yellow probabilities, right? Between 7 and 11. Same probability almost. That's the chance that number of patients coming to the ER is between 6 and 12 people, but not including 6 and 12 in the function. So this is all about Poisson distribution. There are lots of applications to this distribution, same as arrival of the customers to the store, or number of defective product in the production line, number of deaths because of some virus in specific areas. So these are various applications to Poisson distribution. For more information on binomial distribution, please check out the previous tutorial.